Imagine a team of scientists that needs to visit every island on this map.
First by landing on an island with a helicopter, and then to other islands using a ferry. But here's the catch. The ferries can only travel in certain directions, and after every research trip, the scientists must return to the island where their helicopter is waiting. What is the minimum number of research trips needed to visit every island?
Hello, I'm Mariah, and today we're going to solve this Bebras challenge called Island Research Expeditions.
A group of scientists need to study a chain of islands. They have a helicopter, so they can land on any island they want to start their trip. But once they land on an island, they travel using ferries between the islands.
Here's the tricky part. Unlike the Gozo channel, the ferries don't always go both ways. Some ferries can only travel in one direction, just like cars can only travel in one direction in one-way streets. And there's one more important rule. After every research trip, the team of scientists must return to the island where they first landed with their helicopter.
So the team wants to visit every island. They can land their helicopter on any island, travel on as many ferries as they want, but they must end up back at their helicopter so as to travel to a different island which they have not yet visited. Then they can travel again with the helicopter to another island to start a new research trip somewhere else.
Your challenge is this. What is the minimum number of research trips needed to visit every island? The first time I saw a puzzle like this, I tried to solve it in my head and I got completely confused. Writing down the solution step by step really helped, so I suggest you do the same. Take a moment to study the map and think about it. Let's work through it together.
Since the team must return to their helicopter, they can only visit islands where they can travel and still come back again using the ferry. So we need to look for groups of islands where you can travel from any island to another and also come back again to the starting point. Inside these groups, the team can move around freely using the ferry following the arrows, visiting as many islands as possible and still return to their helicopter.
Let's try to find such a group by selecting a random island and see how we can move around. While doing so, we should keep track of all the islands we've already visited, so we don't forget the path we have followed so far.
Say we pick Island D. From this island, we can choose to either go to Island F, E or C. Let's go to F. From F, we can go to E or G. Let's pick G. So that means so far we visited D, F and G. But there's a problem now. We are stranded on G because we cannot take any ferries to D or any other island. That means this is not a correct group.
This is something that happens a lot when you're solving Bebras challenges. You try an idea and then you realize you're stuck and that you need to try other alternatives to try and solve the challenge. That's actually a big part of how computer programmers solve problems too. Let's rewind a bit and consider another island.
Say this time we go to E from F. However, now we have the same problem. There is no way to get back to our starting point, which was Island D, where we landed with our helicopter. So this is also not a good group. Let's go back to Island D. We still haven't investigated where we would end up if we went to Island C. As you can see, if we follow this path, we can easily get back to D by going to Island A and then Island B. So we have managed to find our first group.
But what about the other three islands?
If you remember from our second attempt at solving this challenge, we saw that we could get back to Island F from E. So let's leave Island D and visit Island F with the helicopter. Now we can visit Island E with the ferry and also go back to F, where the helicopter is waiting. So this is also a second group. And what about Island G? Well, we'll have to visit that island individually with the helicopter, as otherwise there would be no way of getting back to the starting island from G, since there are no ferries going out of the island.
So this means we found a total of 3 groups. Some people might think that the team could just take a long journey like this.
C, A, B, D, F, E, and G. This pod visits every island, but there's a problem. At the end of the trip, the team can't return to the starting island to reach their helicopter, so that plan doesn't work. So since the islands form 3 separate groups, the research team needs to go on one trip for each group of islands.
That means the minimum number of research trips is 3. In the world of computers, these round-trip groups are called strongly connected components. Think of a strongly connected component like a round-trip club. In a world of one-way streets or one-way ferry routes, a strongly connected component is a group of places where you can start from any spot, visit any other spot in that group, and most importantly, always find a way back to where you started.
In many networks, like the island map, some paths are one way. If you follow a path from group A to group B, but there is no path leading back from B to A, you have left that club. Inside the club, you can wander around forever and never get stuck because every path eventually loops back. But once you take a one-way bridge or ferry out, you can't get back in, so you have left the club.
But why do they matter? In computer science, we use this logic of round-trip clubs to understand how things are linked together. For example, in social media, a strongly connected component is a group of people that all follow each other. If you post a secret, it can loop around to everyone in that group. On the internet, strongly connected components help search engines find clusters of websites that all link to one another. They are also used in traffic management. City planners use strongly connected components to make sure that drivers don't get stuck in a neighborhood with no way out. And how do we spot them?
To find a strongly connected component, pick a starting point and then follow every path possible. If you find a group of points where you can travel back and forth to your start island, you found a component. On the island map, this is why we need 3 trips. The first trip is the big loop of A, B, C, and D. The second trip is the two-way street between E and F. And the third trip is the dead end at island G.
Thanks for watching and exploring this Bebras challenge with your students. If you try this activity in your classroom, we would love to hear your opinion about it. Please feel free to share your experiences, ideas, and suggestions in the comment section below, so that other teachers can learn from them too. And if your students enjoyed this challenge, encourage them to share their thoughts and solutions in your Microsoft Teams class chat. It can be really interesting to see how different students approach the same challenge. Thank you for helping us bring computational thinking into the classroom, and we hope to see you and your students in the next challenge.